An investigation is underway after a body was found in the Ohio River, and although the autopsy is not complete, the family of a missing man says it's their loved one.
Concerns about the impact of pollution and climate change on the Ohio River today.
You know, today the Ohio River has now been designated the second most endangered river in all of America.
A strange and unsettling event has unfolded beneath the Ohio River, leaving scientists in a state of profound concern. A rift, unprecedented in both location and nature, has opened beneath the riverbed, stretching deep into the Earth's crust and revealing activity that defies prior geological understanding of the region. What initially appeared as a series of minor tremors in the area quickly escalated into a much larger discovery. The Ohio River, a historically stable waterway winding through the eastern United States, has now become the site of a geophysical mystery that could reshape assumptions about the subsurface mechanics of the American Midwest. Before we start, hit the like and subscribe buttons for more exclusive news. The initial tremors were subtle enough to be dismissed as background seismic noise, the kind that occasionally flutters across fault lines or along tectonic boundaries. However, sensors along the river began picking up a sequence of harmonic tremors, vibrations often associated with magma movement rather than tectonic shifts. This anomaly prompted a deeper investigation, and what researchers found sent shockwaves through the scientific community. Deep penetrating radar and seismic imaging revealed a rift forming beneath the riverbed. The Ohio River Basin, traditionally viewed as geologically quiet, is not situated near any major plate boundaries, nor has it historically shown any indications of volcanic activity or significant fault structures. Yet this rift suggests an internal force pressing upward or outward, fracturing the lithosphere in a place where it simply shouldn't be happening. The width and depth of the rift are still being measured, but early estimates suggest it extends for miles beneath the river and sinks hundreds of feet deep. Its formation is not attributed to human activity, such as fracking or mining, which are often blamed for induced seismicity. Instead, the phenomenon appears to originate from deep within the Earth, hinting at larger-scale forces at play. What unsettles researchers the most is the unknown nature of the rift's cause. In typical tectonic environments, such features arise from well-understood mechanisms like plate divergence, strike-slip motion, or subduction dynamics. None of those forces are applicable in the interior of North America in this context. The rift's sharp geometry, combined with elevated geothermal readings along its edges, implies that molten material might be present at unusual depths. Some scientists have speculated the existence of a deep mantle plume, a slow-rising column of heated rock pushing upward against the crust. However, that theory would contradict established thermal maps of the region, which have never indicated such heat anomalies. As the investigation has intensified, data from satellite-based ground deformation systems, typically used to measure volcanic inflation or subsidence, began to indicate minute vertical uplifts along parts of the river's path. Though still small in scale, the implications are staggering. The land is subtly rising around a fissure that should not be there, hinting that some deeper dynamic is at work. These movements are not random. They align with the fault geometry traced by underground imaging, suggesting a coherent system forming under the Ohio River Basin. The geological profile of the Ohio River area adds another layer of complexity. The region is composed of Paleozoic sedimentary layers resting atop the stable craton of the North American plate. These are some of the oldest and most structurally intact parts of the continent. For a rift to tear through this ancient bedrock is akin to a crack forming in reinforced steel. It shouldn't happen without extreme forces being involved. This anomaly has turned the region into an unexpected hotspot for geophysical research, with teams from national laboratories and universities deploying equipment in an attempt to map and model the evolving structure. The rift is also altering the subterranean water tables. Preliminary hydrological models have shown that aquifers beneath the Ohio River are being redirected or drained into this deepening chasm. Water that once fed into nearby tributaries is disappearing into the fracture, causing changes in water levels across multiple counties. While not immediately catastrophic, these changes are stressing ecosystems that rely on consistent groundwater availability. The biodiversity within the river system is sensitive to temperature, flow, and mineral balance, all of which are being disturbed by the geological shifts occurring below. Another alarming observation is the sudden appearance of gas pockets emerging from the riverbed. These emissions, initially presumed to be harmless methane from decaying organic material, have tested positive for helium-3 and other rare isotopes more commonly associated with deep mantle sources. The release of such gases in a region not known for any mantle crust interaction is deeply unusual. It raises the possibility that the rift could be providing a direct conduit from the mantle to the surface, something only observed in places with active volcanic plumbing systems, such as Iceland or East Africa's Rift Valley. Geophysicists are particularly troubled by the sudden appearance of microseismic events clustering around the rift. These tiny earthquakes, imperceptible to humans, form a swarm pattern often seen before larger seismic events or volcanic eruptions. Though the magnitudes are currently low, their frequency and spatial distribution are increasing. This pattern implies that pressure is building somewhere beneath the crust, and the rift could be acting as a pressure release valve, or worse, the early stages of a more disruptive geological reawakening. Adding to the strangeness is the magnetic anomaly observed in the region. Instruments have recorded shifts in the local geomagnetic field near the rift, with occasional pulses of high-frequency magnetic disturbances. These are typically associated with the movement of molten rock or changes in the mineral composition of underground formations. Such readings are rare in sedimentary basins like the Ohio rivers and have led to hypotheses involving underground material previously unmapped or misunderstood, possibly a deep, unexposed ultramafic body now rising closer to the surface. This sudden emergence of a rift in a supposedly dormant area suggests the presence of an unknown dynamic within the North American plate. It could be a localized phenomenon, the result of a hidden weakness in the crust, or it might indicate the initial stages of a larger intraplate deformation system that has gone unnoticed until now. The crustal stress maps generated from seismic velocity models suggest that the region is undergoing tension, but the origin of that tension remains unclear. It could relate to far-field stresses from the Appalachian Mountains or remnants of ancient tectonic scars reactivating after millions of years of quiescence. If the rift continues to widen or deepen, it could change the course of the Ohio River itself. Rivers naturally follow paths of least resistance, and a deepening depression beneath their beds can reroute or fracture them into new distributary systems. The implications for transportation, agriculture, and local economies are considerable. Much of the surrounding area relies on the Ohio River not only for irrigation and drinking water, but also for barge transportation, linking the interior of the country with global trade routes. A shift in the river's course, however slight, could disrupt supply chains, require new infrastructure, and even displace communities living close to the banks. Though the surface remains largely undisturbed for now, subtle cracks have started appearing along river-adjacent infrastructure, bridges, piers, and retaining walls. Engineers have begun monitoring these developments closely, as even minor foundational shifts could lead to larger-scale structural failures. Soil samples from regions adjacent to the rift have shown increased liquefaction potential, particularly where sediment is loose and saturated. In the event of a stronger seismic event, these areas could lose cohesion, posing risks to any structure built upon them. Long-term climatic effects are also a topic of discussion. A significant rift can affect the flow of subsurface heat, altering soil temperatures and even atmospheric microcurrents above. While such changes are often too small to register as weather events, over time, they can influence local ecosystems and migratory patterns of animals sensitive to subtle environmental cues. Already, researchers have observed disoriented behavior among certain species of fish and amphibians in the Ohio River, possibly due to changing chemical and thermal signatures in the water. The emergence of the rift beneath the Ohio River is not merely a localized geological anomaly. It represents a challenge to centuries of accumulated knowledge about North America's interior structure. The traditional understanding of the continent's stability, particularly across the Midwest and Upper South, has rested on a framework in which the ancient cratons are essentially immobile. These foundational blocks of the Earth's crust are considered inert, unmoving zones far removed from the tectonic chaos of fault boundaries like the San Andreas or the Cascadia subduction zone. Yet this rift violates that expectation with its very existence, forcing geoscientists to reconsider how stress and energy may be distributed across supposedly dormant regions of the Earth's surface. One of the first steps in unraveling this puzzle has been the reconstruction of the region's deep geological history. Beneath the modern landscape of the Ohio River lie the remnants of ancient mountain-building events, including the long-eroded Appalachian orogenies and the ghost signatures of supercontinent cycles. These deeply buried structures may harbor zones of weakness, fossilized faults, or even relict magma pathways that, under the right circumstances, could reactivate. The rift's alignment has prompted some researchers to investigate whether these ancient tectonic scars could be playing a role in guiding the current rupture. If that proves to be the case, it would support the growing hypothesis that no part of the continental crust is ever truly dead, only dormant, waiting for new stresses to awaken it. Researchers are now examining the lithosphere-asthenosphere boundary beneath the region with renewed scrutiny. This boundary, separating the rigid upper crust from the ductile layer below, may be thinner or more variable than previously mapped. A thinner than expected lithosphere could allow for upwelling mantle flows to interact more directly with the crust, possibly contributing to the rift formation. Early models suggest there could be anomalous thermal activity at this boundary, though the exact mechanism of heat transfer remains undetermined. It is possible that this part of the North American plate is undergoing slow, large-scale deformation due to stress redistribution far from its margins, a process poorly represented in conventional models of plate tectonics. As data accumulates, one unsettling possibility being considered is that the rift may be part of a much larger continent-spanning structure that has simply remained hidden until now. Some geologists are revisiting seismic tomography data across the central United States, looking for any linear patterns of crustal thinning, deep fractures, or mantle upwellings that might align with the Ohio River anomaly. There are speculative murmurs about a hidden transcontinental rift system, a modern analog to the mid-continent rift, an ancient failed rift that nearly split North America over 1 billion years ago. If such a system is reactivating or forming anew, it would mark a profound shift in our understanding of continental dynamics. Equally fascinating is the way the rift is affecting local magnetic and gravitational fields. Earth's crust, though solid, is not homogeneous. It varies in density, composition, and magnetization depending on its history and mineral content. The rift is altering these parameters by either exposing deeper, denser rocks or shifting the distribution of materials underground. Gravimeters positioned along the river have begun detecting minute changes in gravitational acceleration, suggesting mass redistribution beneath the surface. Similarly, magnetometers have picked up fleeting shifts in polarity, fluctuations that do not conform to expected diurnal variations or solar activity. This has raised questions about whether the Earth's magnetic field itself is being locally distorted, and if so, what that might indicate about the material composition of the newly forming rift walls. One of the more controversial avenues of research is the possibility of deep biosphere exposure. The crust of the Earth, particularly in deep sedimentary basins, can harbor ancient microbial ecosystems adapted to extreme pressures and chemical conditions. As the rift breaches these layers, it may create pathways for these extremophiles to migrate or even reach the surface. Already, water samples taken from deep within boreholes near the rift have revealed strange microbial signatures not previously cataloged in North America. These microorganisms, while not dangerous to humans, could represent a form of life that has been locked away from surface ecosystems for millions of years. The implications for evolutionary biology, astrobiology, and the search for life in extreme environments are profound. From a structural standpoint, the presence of such a rift poses long-term engineering and architectural challenges. Urban centers near the Ohio River are being advised to begin re-evaluating their civil infrastructure with new subsurface risks in mind. Deep piling foundations, tunnels, and large dams may no longer be as secure as previously thought. Engineers are developing new methods to test the integrity of soil and bedrock beneath key transport and utility hubs. In particular, hydroelectric facilities and water treatment plants are now under additional surveillance to monitor how their foundations might shift or settle due to deep crustal disturbances. Insurance companies have begun to re-evaluate their actuarial tables for natural disasters in the region, factoring in the unknown variable of an active rift in an area once deemed geologically safe. There is also the matter of induced stress fields and their interaction with anthropogenic activity. As the rift opens and redistributes pressure across a wide area, it could affect how existing faults or fracture zones behave, even those that have been dormant for centuries. This concern becomes even more pressing when considering how deep waste injection wells and subsurface carbon storage efforts might respond to the new stress environment. Fluids pumped deep into the earth can lubricate faults or alter pore pressure in ways that exacerbate seismic risk. With the rift changing the baseline conditions of the region, previously benign industrial operations could become significant hazard multipliers. The field of environmental science is also grappling with potential consequences. A large rift beneath a major river can alter groundwater flow patterns, nutrient cycling, and even sediment transport. The hydrological equilibrium of the region is delicately balanced. Rivers, wetlands, and floodplains work in tandem to regulate seasonal water availability and quality. As the rift begins to reroute subterranean flows, the composition of river water could shift, leading to elevated mineral content, temperature anomalies, or changes in dissolved oxygen levels. Fish and aquatic plants accustomed to a specific range of environmental conditions may find themselves in hostile new waters, leading to migration or collapse of key populations. Invasive species, always opportunistic, could exploit the chaos to gain new footholds in weakened ecosystems. The implications also ripple outward into the domain of climatology. A sudden change in the subsurface heat profile of a region can affect local microclimates. Heat released from deeper layers of Earth through fissures can create pockets of warm ground that subtly influence air temperature, humidity, and pressure. If sustained, such changes can create new weather patterns or destabilize existing ones. For example, a band of warmer soil along a major river corridor could affect fog formation, storm track behavior, or even frost timing, factors that matter greatly to agriculture and seasonal ecology in the region. While the rift is still relatively young in geologic terms, its rapid development has led some experts to draw parallels with the earliest phases of known rift valleys around the world. The East African Rift, for example, began as a slow separation process within the African plate, eventually leading to volcanism and the formation of new crust. Though no such volcanic activity has been recorded in the Ohio River basin yet, the conditions leading up to rifting, crustal stretching, fault propagation, mantle melting, are all present to some degree. This prompts questions about whether similar phenomena could eventually manifest here, albeit over longer timescales. If so, the region could transition from being a simple interior basin to a proto-rift valley, complete with volcanic systems, fault-block topography, and new sedimentary regimes. Researchers are now modeling potential surface expressions of the rift as it continues to evolve. If crustal extension continues, the land on either side of the rift could begin to subside or uplift asymmetrically. This might eventually form escarpments, low ridges, or basin-like depressions along the river corridor. Over time, such topographical shifts could influence how rainwater drains, where vegetation grows, and how human settlements expand or contract. Communities might face the unexpected challenge of adapting to new landscapes that slowly but steadily rise or sink beneath their feet. Among the more esoteric but no less important concerns is how the rift might impact Earth's rotational stability. Large-scale mass redistribution within the crust and mantle can, in theory, cause minute shifts in the planet's moment of inertia. While the changes brought on by the Ohio River rift are currently too small to detect on a planetary scale, sustained or accelerated movement could eventually register in global geodetic measurements. These shifts, though minor, can affect satellite positioning, GPS calibration, and long baseline astronomical observations that rely on precise Earth orientation parameters. The discovery of the rift has also ignited philosophical and existential discussions among scholars of geology and planetary science. The idea that something so massive and transformative could form in a place long considered stable serves as a humbling reminder of Earth's dynamism. Human civilization often builds its assumptions on the perceived constancy of the environment, but events like these challenge that foundation. They remind us that beneath our cities, roads, and farmlands lies a living, shifting world, one capable of change on scales and timelines far beyond human experience. There are already calls within the scientific community to establish a permanent research observatory near the rift site. Such a facility would serve as a multidisciplinary platform for studying crustal deformation, deep biosphere interactions, geochemistry and hydrology in real time. If approved and funded, it would become one of the few such observatories located in a continental interior rather than along tectonic margins. Its existence would acknowledge the need to watch not only the Earth's edges, but also its heart. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on the Ohio River Rift? Will it trigger something bigger? We want to hear from you. Thank you for watching and see you next time.